So I wanted to show you this really cool robot riding bicycle, but I'm having trouble getting that, and there's a Flickr movie. There's a Flickr picture. Anyway, having trouble with this. I'll let you all try to find the video. It's really a cool video if you can find it on YouTube of this robot riding a bicycle. I think I talked to you last time about Android and robots, so it's kind of a robot space for this week. But the first couple of seconds of riding a bicycle is crazy unstable. It's like flying. When you're just taking off or just landing, it's the craziest time. Almost all the crashes happen during that time. All the unstable conditions. You can't turn too much, all those things. True for riding a bicycle, and you might remember from your days of riding a bicycle. So this robot handles it very well on those early stages. Pretty cool. So today we're talking about combinational logic blocks. This is what we ended up last time at the summary, although most of you are already closing up. We're now lecture 26. And you can essentially go from anywhere to anywhere. The only thing of note is there's no arrow from a truth table to a gate diagram. So the way you think about this is, okay, I have a truth table, all the ones and zeros. You don't just build gates out of that. You typically create a Boolean expression out of that, either sum of products and then massage it, get your hands rich in the Boolean algebra massage oil, and then you massage it to be simplest form, and then you make gates out of that. But we just typically don't go from the truth table to a direct gate diagram without having some kind of a Boolean expression in the middle of that. Okay? But everything else, you should be able to go from A to B and make that happen. It's pretty cool. So today we're talking about something that's really cool as we're moving up. We started really low level at the electron level 4 lectures ago, and we're moving up now to start to build bigger and bigger things. You now have state elements, you now have combinational logic circuits. As we go larger, as we go to larger blocks, as we start to build a MIPS machine, you're going to see we're going to need some of these things here. So these are things that you might have realized we might need already as I start building my CPU. And then Mike will take it over and finish it out as we do the CPU data path and control. So this is the first big block that's important, and it's important in every computer engineer. In a way, these 4 lectures have been computer engineering. It's building how do you build this stuff up if you're going to build it yourself. And this multiplexer, otherwise known as a MUX, is a fundamental building block. And this multiplexer, I think of as being a traffic cop. Okay? You have 280 and 101 feeding in near my house in Daly City. They both feed in, and then they split off. But what if 280 is all crumbles down? Then 280 and 101 have to feed into one route, which is 101 south. So how would you do that? Well, you'd have some very tall traffic cop saying, okay, you 8 lanes of 101, you can now drive 101 south. Come on in. Okay. Okay, so you have it. And then I'd say, stop, all you 8, and now, okay, you at 280, you go. It's the same traffic cop thing, but I can not just move for 1 lane, but for 8 lanes, or for n lanes. That's what this MUX does. So the MUX has the signal, which is the switcher line. S has, in this case, 1 bit. And it's 1 bit because I'm only choosing among 2 different options, A or B. A or B have however many bits they have. In my example of 101, I didn't care how many lanes 101 and 280 was. I just care, they just have to at least match up, N, N, N here. So this is a muxer called 2 to 1 guy. Okay? So here are n instances of a 1-bit wide mux. Okay? So here's a 1-bit wide mux. So just the simplest case. That was a generic mux. That was a 2-input mux. Here's a 1-bit wide mux. How many rows in my truth table? I'm going to go to this part of the class. Give some hands. Yes. 8. How do you get 8? 2 to the 3 because there are 3 inputs, A, B, and S, and that's correct. And there is your truth table. Okay? So you're going to look at this and you say, well, that's interesting. I now know how to go from a truth table to a circuit diagram. Right? We know that. That's part of the first page. So let's do that together. Okay? First, I'm going to do my sum of products. C, the output is true only when these 4 terms are true. You always put a bar of whenever it's a 0. You basically read it off. So I need a 1 here, which is not S and A and not B, and there's your first term. You do that 4 times, you get this. You do some Boolean algebra massage oil, and you end up getting this really simplified term in the bottom. And what's so cool about the simplified term in the bottom is it actually reads like English. For example, let's read it together. This says not S and A, or S and B. And that's actually what the MUX is doing. When S is true, when S is false, 0. When S is 0, it's A. And guess what? When S is false, 0, then not S becomes a 1. That goes away. This term goes away, and you get A, which is exactly what's happening. C is just A. I don't care what A is. It's just A. And when S is asserted, S is true here, then not S is false. That term goes away. S is 1. That goes away. You just get B, and C equals B, just as you said here. Isn't that kind of cool? So at the end, it's in a way, from now on, when you see muxes, stop going from the sum of products model. Just write this. Right? You now know if I gave you, say, a 4-input mux, how to do it. By just going straight to the goal. Just straight to the simplified form. Questions about this slide? Pretty cool, right? Yes? The terms everywhere C is 1. Exactly right. Yeah. The way you go for sum of products, you say, where is C1? And you can write out all those terms, and it could be a lot of them. Could be a lot of them. Okay? Yes, go. Very good. If you have 4 inputs, you need 2 S bits. Exactly right. Yep, exactly right. Other questions? Okay, so how do we build this? Well, you can see how to build this. It's pretty simple. I've shown you that already. This is a review. That's nothing new on this slide, right? I just take an expression and make my circuitry. And there's my C. That's pretty cool. So you now know how to build a 1-bit wide mux. That's pretty nice. Ooh, this question just came up. Now I have a 4-to-1 multiplexer. What do I do there? You can imagine what I do there. Okay? A, B, C, and D are single-bit inputs. I don't have any slice across those lines to tell me how wide they are. They are 1-bit wide, therefore. And now what I usually do, by the way, this is really important. One of the things you might not have noticed from this picture of this is that I actually have to write on the mux itself what's the 0 and what's the 1 input. Otherwise, I don't know if I plug this thing in and I say, okay, S is 0, who gets to drive the line, A or B? So I always have to write on the mux which one is 0 and which is 1. For the first time, you have to have a DQ to know which way to spin, which is the input, which is the output of your flip-flop. Same way with here with the mux. You got to have a 0 and a 1 to know which way, who's going to be driven if I set S to 0, right? So now if we go to a 4-bit input, I have to do the same thing here. I have to have all the possible combinations of my S's on all the inputs so I know who wins if, say, S is set to 3 or something. Yes, question?
So the mux physically works the same as like,
that. Physically, the mux is just that. That's all it is. It's just a truth table. It's just figuring out who wins. It's kind of cool. And it's not state. It's a combinational logic circuit, right? There's no clock in here. Okay? Very simple. Okay? So, here's my 4-to-1 mux. How many rows in the truth table? Somebody in the back now. I'm focusing on the back only. Give me some back love here. How many rows in my truth table for my 4-to-1 mux? Yes? 64. How do you get 64? 2 to the 6. How do you get 6? 6 total inputs. Exactly right. 6 inputs. 4 data lines, 2 signal lines. That's 6 inputs. 2 to the 6 is 64. Okay? So, here's my expression. Notice I don't even go into the sum of products for that 64 line. Like, how silly would it be to write a 64-row truth table and have to turn those terms? I say go straight to the source. Go straight to the answer. Why wait? Right? Why beat around the bush? Jump right in there. Okay? So here's E, the output, which is, and you can just read it, just like I said before. Look, A is asserted when not S1 and not S0. And the nice feature about this, you can even read into this, which is only one of these guys is ever going to be true. For any particular pattern of S1 and S0, only one of those terms goes live, which is exactly what I want. Whoever the S's say to drive that line that day, the answer is it's A today, or tomorrow it's D. But it's only one of them, and that's kind of neat. So already you're learning how to interpret these Boolean expressions to have some meaning. They're not just kind of a set of symbols. They actually have some meaning. And I know that because I have every pattern of S's down here, S1 and S0, only one of those is going to be active at any one time, and the other ones will always be 0. That's kind of cool. So you can go straight from this to that. And if I give you this, I'd say, hey, here's some random circuit. What do I actually mean? Probably I'm meaning mux in there because one of those guys is going to be winning. Right? Good. Questions so far? Pause for questions. This is kind of fun stuff. This isn't kind of ground-shattering stuff. So How could I do this? Here's my truth table. It's really complex. I have to now build a custom circuit to do my 4-to-1 mux. Or is there a more clever way to build it out of things that I know? Almost the MIPS mentality of, I want to build this polynomial multiply. Rather than add a new instruction, I say, can I build it out of what you've given me so far? So can I build this 4-to-1 mux out of, oh, I don't know, some of the things you've seen in previous slides? And how would you wire it? I see a nod. Give me some love. How would I do it? How would I wire it together to make my 4-to-1? Maybe anybody here. Go ahead. I can use 3 2-to-1 muxes. How would I wire them together? I love it. First two share the S0 input, and then? And then the next one takes the output from the first two. I love it. What's your name? Emily. Emily. Perfect. Exactly right. Let's hit it. Think NCAA tournament. Here's what exactly she said. Emily said, these first two guys share S0, like an early competition, like round 1 in a Final Four. And the winner of round 1 in the Final Four goes on to the finals, and Brent Musburger, does a thing, and now you've got S1 determines who the winner is in the finals. Love it, right? Big trophy at the end. Yay, you won the S competition. You get to drive the E line here. Question in the middle. Yes? Do you ever have an odd number of inputs? What do you guys think? Sure. What would you do? Let's think. Let's go back to this. What would happen if rather than A, B, C, and D, I just had A, B, and C? Could I do it? Yeah.
Well, if C was the one by itself, it would just go through. It's like in a tournament, right?
It's like a tournament. It's like C automatically got a bye. See, I'm making the connection to basketball still. See, this means, like, imagine no D. Well, C would just go straight through. It's as if there were a D, and C won the thing by default because D's bus broke down and he didn't get to the game. You see that? Good stuff. Okay, so that answer. Yes, Christine in the front.
Then in that case, wouldn't that mean that P corresponds to 2 different indices? Like, because S and S... Correct. C would correspond to those different indices. That's right. It's as if you had a D, and maybe there's a way to kind of simplify that. If I had, if I say, build the actual gates, if I know there's no D, can't you be a little simpler? You might be able to be simpler in that case because you don't have any of those D cases. Exactly right. Yeah. By the way, you saw a truth table that I had. Didn't my 3-input counter have 6 rows, or did it have 8? I'm trying to remember. Maybe it had. I think I just had 6. Remember, I had 3 states. Each state had a 1 or 0. I think I had 6 rows before. So you can have truth tables that don't have a power of 2 number of rows. No problem, right? So you do exactly that. Right hand, yeah.
So in that case, you could just get rid of that multiplexer.
Yeah, exactly right. You wouldn't even use a multiplexer. C would literally just plug into there.
So,
exactly right. And I'd save some circuitry, it'd save some transistors. Exactly right.
Just as a engineering question, what would you do if S0 and S1 were both, say, 1?
What would you do in that case if S0 and S1 were just 1? Well, it doesn't matter S0 because C goes through here. S1 is going to control, and the answer is C gets to drive it. If you wire it like that. Right? I mean, because think about that.
If you wired it, I agree. What would you choose to use it?
I would never get to that state. I mean, right? The whole point is that you maintain the whole system, and I build a circuitry in which S0 is supposed to have value, S and S1 are supposed to have the values 0, 1, and 2, never 3, and you're giving me 3. So you're asking me something outside of my spec. My spec says I can handle those 3 cases, I only have 3 inputs. Yes?
If you were doing some kind of time division multiplexing and you're getting 2 different data in on like A and C at the same time, don't you want to do something to preserve the other data so it comes in later? It was like multiplexing.
I think you're confusing time division multiplexing in the higher level software level with just simply choosing between different circuits. We don't worry about timing in this kind of thing. This is just a untimed system. There's no clocks in here. I think you're thinking about the other phrase that has multiplexing in the word. Yeah. Are we wasting some gates? Here's the best part. If we were actually setting this off to be fabbed, I would say, here's my truth table. Here's my expressions. Internally, like in Mathematica, it's going to say, here's the truth tables, here's the way to do this. But if you're wiring this from the simple point of view, this is a way of thinking of it. But I'm sure that there's a simpler way to looking at those actual 64 rows and making simpler circuitry to do that. So it's nice to be able to do this, because we're going to see a little later why this is useful when I do our adders. We'll see that in a second. Yeah?
What if I want to build like a 8-bit like wide like a box, then will
8-bit wide, so 8 inputs. I'm choosing for a moment 8 inputs, you mean?
like 8-bit wide.
Oh, so each of these guys are 8 bits wide, you mean?
Yeah, so then
So actually there's two variables. It's like two-way 8-bit wide is what you're going to say, probably. It's like the first picture, right, which had 2 lanes, 101 and 280, each 8 bits wide, but only 2 different inputs I'm choosing from among.
Yeah.
Okay?
And then n wouldn't does n keys work there? Or like S0 and S1 would be like 1 bit.
Yeah. It would just be a vector. It would be the output capital C, which is 8 bits of it, equals not S times the vector A plus not S, or S times the vector B. It would just be that each of those guys happen to be 1 bit, they're now 8 bits. It's all the same. It's 8 parallel equations, all the same thing. Remember that? Good question, actually. Okay, so let's go to here now. So now that we've seen the mux, it turns out that you can be even more abstract with those signal lines. Rather than using those signal lines to choose from among of several different wires, why not let those signal lines tell you what your box is going to do? Here's a box called an ALU, an arithmetic logic unit. And rather than say, okay, choose from among the wires, the simplest case, use those signal lines to tell you what op you're going to do. How about that? You can see how useful that might be as we start to try to implement real MIPS. And real MIPS is going to have adds and ORs and ands and subs. And we're going to need to have one box that basically has signal lines that say, if the wires say this, then do that operation. If the wires say this, do that operation. Those wires are driven by the leftmost bits in my opcode, maybe my function. See how we're starting to connect it from actually running real MIPS, where what you're supposed to do is encode in those bits of the operation, the opcode, and the function line, to actually those lines going to be ones or zeros, and that's going to drive something inside my MIPS interpreter, and that's going to drive the ALU at some stage down below me. Isn't that really cool? So you can see why this would be useful from like thinking of, let's go back to now the pre-SDS days where you didn't know about how we built this stuff. Yeah, we might need some hardware to be able to do someday an add, and someday an OR, someday an AND, and someday a sub. Now you realize those signal lines will then eventually be driving that S line. Isn't that kind of cool? So that's the idea. This ALU is now a generic operator, which is able to work on 32-bit wide inputs. That's pretty cool. And whatever I tell the S to do, that's what it does as my operation. Isn't that awesome? Okay? All right, question. So now, this is a very simple way to do that. Let's take a look at how this works. Remember my codes here. 0, it's add. 1, it's subtract. 2, it's AND. 3, it's OR. Okay? So let's look at it here. 0, it's add. Let's see. Add 0. Okay, well, that's this line getting driven. And, it's going to lose that battle because it's going to be this line. Okay? And S0 must be 0. That means add. So we agree that 0 is add. 0, 0. How about 0, 1? Same thing. S is going to only choose from this side, and then S0 will be 1, and therefore this will be a subtract. How about 2? Well, if you look at a 2, 2 says this guy goes high, so I ignore the add subtractor, and the AND and the OR are both active, but the S0 lets the AND go by, and when it's 1, 1, it's the OR that wins. Now, here's the critical question. Parallelism in hardware. When it's set to S0, S1 are 3, which means the OR is driving all the lines, does the add subtract go to sleep, and does the AND go to sleep? Just basically you wake up and say, okay, like in C code you'd have, if it's this case, then do that code. Else, if this case, do that code. You wouldn't be doing all of them at once. It'd be some else case or a switch or something like that, like in C. But we're hardware, folks. Does my add, subtract, and AND go to sleep? No. It's always doing its work anyway. And just at the last second, it says, I've built this adder. And you say, yeah, I don't want that. I want the OR today. And you're like, but I built the adder. I have your answer. I did all the hard work, and I did my overflow. And yeah, I feel like having an OR today. Oh, man. You see? So this is important that you remember that hardware is always doing its work. Those circuits are always doing their work. They're just being ignored at the end. Somebody's going to win at the end. That's who gets chosen, right? Question, yes? Ah, good question. How does the multiplexer know? Class, when does the multiplexer know? It doesn't know. It doesn't know. You have to set up the system so that you account for the longest delay through each of these blocks, as well as the delay through the multiplexer, and after you wait all that time, then your answer is guaranteed to be ready. But you can't before that. That's exactly right. Okay? Other questions? Yes, in the back. Okay, good question. Since all of them are running, are we talking about just wasted energy of transistors flipping, flopping? By the way, transistors use power when they change states. So you actually want them to not change states. So you actually are using power when you change a state. So they actually are. Bits are flipping from zeros to ones if the inputs are changing from what they were last time. So yes, you're changing states. But is it only wasted energy, or is it also wasted time? Talking about your time factor. Well, here's an argument. Let me go for based on what I just said a second ago. You had to wait to guarantee the right output. You have to wait till the slowest box up here is done, whatever the slowest of these three, plus the longest path, which might be going through here and going through here, even if you knew that only this guy, only S1 was going to choose a 0. So the answer is yes. Because you built it this way, you always have to wait that longest time. You set your clock to some value based on the longest ever time, even though that particular time you weren't going through the slow box. The slow box was the OR. And you also had 2 of these muxes in the way. And today you were going to do a sub, and that was going to be really fast, let's say. Turns out that actually AND and OR faster than the sub. We'll say that in a second. But let's say the add sub was really fast. And that day, that particular clock pulse, I was asking for the add sub, which is faster than these blocks and doesn't have to go through 2, only has to go through 1 mux. I'm sorry. You had set your clock based on the slowest possible thing, so you're wasting time and energy. The answer is both. Good question. Yes? Why do you put the multiplexers before the operators? What does that mean? You could do that. I think, so the answer to the question was, can't we be smart about it and say, lock the values of A and B and say they don't change if you're not going to use them in the first place? I love it. That's an optimization that would actually work. I mean, you're spending some more money on maybe other muxy things and some more stuff. So you're spending some energy on larger die, more transistors. So there's a factor of just having a transistor around is going to cost you some power also. But maybe you can save some power in terms of switching. If these guys are switching up, you say, like, listen, I'm going to ignore my add sub, so don't even let the data change. Maybe have another guy that holds it and only reads in the new values if they're going to be different and going to be using that line. I can see that. I can see that. That's a small optimization. Yes, questions in the back. Two neighbors. Go ahead.
Like you said that it's not exactly energy efficient. So why is it that all 4 have to be working at the same time? Why can't one, like the other 3 be asleep?
Why can't all 4? Why can't 3 be asleep? That's not how hardware works. Hardware works. It's just the signals are changing and voltages are changing and transistors are ready to be able to receive the new things. I mean, it's like unless you explicitly dampen or pinch the outputs and make them not change if they really are changing out there, like kind of buffer them away from the world like you do for your 5-year-old. The world has all this war and hatred. You kind of buffer them so they don't see the change. It looks like the same day as yesterday. You could try to do that, but you're wasting, there's going to be spending some more money on transistors and space and that to do that buffering. Does that make sense? But hardware is just all parallel all the time. It's wonderful. Yes, go.
Since we're splitting the input into like n number of ways, we also have to amplify it so the signal doesn't.
Very good question. If I split this n ways, don't I have to deal with some amplification? Each of these blocks is going to have the power to drive a certain fan out. So all we're going to make sure that as I have my thing wired, I have that fan out not exceeded. And here I have the fan out be able to handle, there's only 3. Each of these wires, each of like bits of A only drives 3 wires, right? Each output bit from wherever it's coming from only in this particular diagram. So assume that the fan out is within the spec in terms of that. But you're right, there is a factor to this fan out and you have to factor that into the design. Especially with clock. Your clock goes everywhere, right? Your clock powers all your state circuitry. You have to worry about that for the clock. That's exactly right. Good questions. Yes, last one. Aha, good question. What's your name? Rachel wants to know how the S0 makes the add subtract wake up, and let's actually go into that. That's the next couple slides. Well done, you're a plant. Excellent. So we're going to look into as Rachel suggested, let's now hit the add subtract block hard, because you know about this guy. How do you do a 32-bit ANDer? I mean, how do you do a 32-bit ANDer? How do you build this box over here, the AND guy? Is that even worth talking about? Does bit I affect bit J on this AND? No. It's a bitwise operation. So guess how we build this? 32 ANDs in parallel. Each for bit I, and bit I outputs bit I of the output. How about the OR? Same thing. Not even worth talking. Not even worth a slide. Okay? So, good question. That's how we build the AND and OR. Add and subtract is the only thing that's even interesting here. Let's hit that hard now. So let's design it. We've got, look at this thing. Here's my add subtract block. How many inputs? 65 inputs. So let's go to the truth table model. Ready? Go. No. Psych. We are certainly not going the truth table technique for design for this thing. We have to think of something else. Why did I bring up the mux idea? Because we build the mux. We said, if we had a 1-bit mux, can we build an n-bit mux with this 1-bit mux? And the solution was, Emily said, let's hierarchically cascade them, and I blessed it. Okay? So now, can we do the same kind of thing? You're obviously not going to do the 2 to 65 table in sum of products. Ridiculous, right? So how do we do this into smaller problems? Can anybody think about that? How will we do this? What's the elemental block of building our 32-bit adder or subtractor? Yes, Christian. Like a 2-bit adder or like a 1-bit adder. The simplest case is the 1-bit adder. It's easy. You need 32 of them. Okay? So let's look at the 1-bit adder. Okay? Now, a 1-bit adder is this. I have A is 0 and S is the sum. Okay? I also might have some carry out, because I have like 1 bit in each. There's a box. And now there's 1 bit out, but I also might have a carry out. I might, it might be more than 1 bit of output. Right? 2 1 bits could be 2, and that's 2 bits of output. So I might have to have a carry out. So S is my sum. You can see this here. If I add 1 and 0, I get 1. 1 and 0, I get 1. 1 plus 1 is 2. And this is really the lower bit of the 2, and C is the higher bit of the 2. So that's my carry out. And so now, here is, I should ask you what those are, but you could probably guess. That's an XOR, that's an AND. You should all know that by now, but if you didn't, that's an XOR and an AND. Okay? So there's my 1-bit adder. Woohoo! We're done. However, there's 3 characters that is the, I'm lying to you, but that's true, but there's 3 characters that make that true here. The LSB. This is the least significant bit. The smallest bit, the 1's bit on my adder, that's correct. I only have an A and a B coming in, and I have 2 outputs, an S and a C. What's my next bit over? My next bit over going to have an A and a B, my C out, my sum. What else? C in, because I got to be able to handle the fact that the 1 bit might have had a carry out. So now I need another column of another row of 4 more rows of my table. Another input, which actually makes it now 3 inputs. Therefore, it's 2 to the 3 or 8 different rows of my table. And you can see this is all addition, right? So the sum of all these numbers in binary is these 2 numbers if you flip them in those things. So 1 plus 1 plus 1 is 1 in the lower bit and 1 in the higher bit. Okay? So now don't look at your slides. What is the equation here? Do you see anything that you've seen before in SI or CI plus 1? We are this close to building this thing and making it work. It's really quite cool. Run it. SI is still XOR. Let's look at it. 1, 1, 1, and 1. Correct. SI is still XOR. What is CI plus 1 somebody else? Henry. Majority circuit. Bam. And guess what? I gave you majority. I kind of gave the answer before you knew why it was going to be useful. Majority circuit. Isn't that cool? That the 1-bit adder that we use in every single adder in every single computer ever, since the first HP calculator to the highest order thing, is really at that level of the 1 bit is really the majority circuit determining whether the carry out comes out. Isn't that kind of cool? I think it's kind of cool. So it's not just we're doing votes of who's going to pick up the takeout. It is actually doing the carry for us. Okay? And you remember the majority circuit was exactly this expression. So questions about that? That's kind of cool, actually. All right, so now that we have it all, we have our LSB is the simple case of the AND and the XOR. The generic case of my 1-bit adder is an XOR and a majority circuit, and I'm ready to go. So there is my 3-input XOR, there's my majority circuit, there's my average bit of the adder, and I'm ready to go. So, there it is. I love it. I love it. Now, let's think of, just for a moment, let's take a look at this picture and see what you tell me. What seems strange about this picture in terms of how do I take the idea that that 1-bit adder might have a 1-bit adder propagation delay? What do you see right here? What starts to bother you about that? If I have a 1-bit AND and a 1-bit OR propagation delay, a 32-bit AND and a 32-bit OR is still a 1-bit propagation delay. It's the same number. It's whatever that was for 1 bit, it's the same as 32 bits. I can't even look at it. I can't even look at it. That's how bothered I am by what's going to happen, what the answer to this is. I will look at you. You tell me. I won't even look at the screen. It's bothering me so much. What do you see here? It hurts, right? It hurts to look at it. Yeah, in the back. Go. You wind up adding the propagation delays for every bit you have. Because you have, it's sad, it's called the ripple carry effect. And you end up having, what if you had the lowest bits has a carry out? And what if that causes a ripple of a carry out in the next guy? And you keep having these ripple carries, you got to wait for each of those guys, those ripples to take effect. I'm not ready. If I say after one adder delay, one 1-bit adder delay, I say, hey, what's your most significant bit? The person who's the guy there, that most significant adder says, can't tell you yet, buddy. Like, what do you mean? But your A's and B's are stable. Your A sub 31 and B sub 31, they're in. Get it ready. Guys, like, see that C n minus 1? Got to wait a little bit longer. Like, what do you mean? Well, because it just started to happen that the propagation delay for that carry out happened at the lowest, at the LSB. And then another propagation delay happened at the second to that, which is the all but LSB. And you wait 31 more propagation delays for my 1-bit adder until I finally get that. That hurts. That hurts a lot. So I'm not going to look at it. That's how angry I am at this. No. So it turns out we're going to actually have clever wiring and clever algorithms in order to try to ameliorate that problem. Because there's no way I'm waiting 32 add delays. There's no way I'm slowing my clock down to handle that. So we're going to see really clever ways to try to get that answer from all the way over there to all the way to the front as fast as possible. We're going to see some really clever things. I won't talk about it in this lecture, but you can look up about those clever things to do to handle that problem. Okay? It's good stuff. So, what about the overflow? What happens in overflow? Let's talk about that for just a split second, because this is actually some cool stuff. And it's also where people get kind of confused. It really is, the meat of it is this picture. If you get the meat of this thing, that's it. The overflow is really just a little bit of juice on the top. And unfortunately, I spent like 5 slides talking about this little bit of a juice. But let's talk about it in case we wanted to actually think about it. Is overflow this last guy? Rohan.
Yes, if it's unsigned overflow.
Excellent. If I'm unsigned, these are just raw unsigned numbers, then it is. Okay? What if they're signed numbers? All of a sudden, things change a little bit, right? It's not so simple if they're signed numbers. So let's actually look at the lowest 2 bits if they're signed numbers, okay? So this is a 2-bit signed number. So remember, let's assume I'm only adding 2 bits, and that's it. And I want to study this higher order guy and how that is. Remember, before we're just thinking about it's just the output. If this is an 2-bit unsigned number, it's just C2. We agree? You can't fit this guy into 2 bits, so C2 is going to have some energy, some 1s popping over, therefore my 2-bit unsigned overflow. But if I have unsigned, let's look at that. If I have signed, let's look at these 2 guys. And look at this exact higher bit. And this is a little bit complicated. Okay. I have 4 different values for what those bits mean. And you might recall from lecture 2 or 3, here's how you would encode a signed number in 2 bits. If it's 1, 0, it's -2. If it's 1, 1, it's -1. One of the ways to remember, by the way, in general, for 2's complement is whenever you have all 1s, it's -1. Just kind of easier to remember that. Okay? So I know that 1 is minus 1, therefore when before that is minus 2, you know you have one more negative number than positive number. If you remember all these details, 0 is always 0, and 1 is always 1, because it's the same. If the leading guy is a positive, then the unsigned and the signed are the same value. So that's what I got. What if I add this to other ranges of numbers, which is, what if I add minus 2 to the other possible 4 answers, minus 2 plus minus 2, or minus 2 plus minus 1, minus 2 plus 0, minus 2 plus 1. Which of those things cause an overflow? And here's the answer. 0 plus anything is not going to be overflow. If I can store it in 2 bits, I add 0, I can still store it in 2 bits. You agree with that one, right? When does 1 overflow? Only when it adds to 1, right? When the positive guy comes out. When is minus 2 overflow? Well, that's the smallest negative number if you add it to any negative number. And so complementarily, or said the other way, is minus 1 only overflows if it's added to minus 2, because it pushes the minus 2 over the edge. Okay, you got that? You agree with that? You kind of have to get this before we go on to the next part. All right. So now, look at the highest adder. We're going to call C1 carry in and C2 be carry out. We're looking at this last guy. Because what the cool thing is, by looking at this 2-bit guy, it's going to be the same property for the highest 1-bit adder of the 32-bit number. So whatever we conclude here was the same conclusion that will hold for our 32-bit guy. Okay? So now, let's look at it. When does overflow happen? Overflow happens when, let's look at the case again. 0, 1 is here, so this is like A is 0, 1, and B is 0, 1. Okay? So add 0, 1 to 0, 1. What happens? The 1, 1 comes in here. There is carry in here, right? Because 1 plus 1 is 2. Therefore, there's carry in here. But these are zeros, so there's no carry out. So in the positive case, I have carry in, but no carry out. Okay? Now, let's go to the negative cases. The negative cases, look here. If I add minus 2, which is 1, 0, so A is 1 and A0 is 0, and I add that to either minus 2 again itself or to minus 1, and what I get is there's never carry in that case. Let's look at that. If I add 0 plus either 0 or 1, I can fit that in 1 bit. Therefore, no carry in. But look at this. The high order bit is a 1 there. So I do have carry out. Notice how quiet the room is? Okay. What that means is we're at the case where I'm trying to get this little detail thing, and nobody's either paying attention or cares, and it's probably a mix. And that's fair. This is a very small remote point. But I want to make sure, if you really want to know how this all exact thing works for signed numbers, this is the whole thing. To explain, I can't just explain an adder without explaining how the overflow part is handled also. So I've got to kind of go to the details of this. So it's the case when, basically, carry in but no carry out, they're both positive and I have overflow. Carry out but no carry in, they're both negative and there's overflow. But only in those 2 cases. So give me something that says, give me an expression that is carry in but not carry out, or carry out but not carry in, but not both and not neither. Give me a gate for that. Go. XOR. Bam. What operation? XOR. That's it. We've now completed the loop. We've now put the icing on the cake. This is the whole picture. This, my friend, is one of the coolest pictures. Let's not look at it. There's my carry out and carry in for my overflow handling, right? That's the case for the signed numbers. We know that it's just carry out for the unsigned numbers. You say, well, what's happening here? This is so cool. I want you to appreciate how cool this is from the hardware point of view. I wanted to do an adder and a subtractor. That's what not Emily, but Rachel. Rachel wanted me to do, Dan, tell me this add subtractor thing. How does this S control it, right? That's what you asked earlier. Here's my slide. S, this sub. When sub goes high, I want to do a subtract. When sub goes low, there's my adder. Okay? So that's the lowest bit of the S0, which is before the controlling the whole thing. Here's what's so cool. You do an adder, what happens? Well, this is I wired things for the adder. I didn't talk about a subtract at all. In the last 30 minutes, I'd never said the word subtract. I said adder. So I built a circuitry with adder, with that ripple carry and all that stuff. So here's this thing. And now I say, I want to someday subtract A minus B. Well, I obviously have to build a whole new set of circuitry to handle the ripple subtractor. A minus B is also what? A plus negative B. Is there a way to make B negative? Flip it and add 1. This is so cool, I'm telling you. Who's got the neck? The little pimples in the back of the neck are all popping up. This is good stuff, right? The hairs. Not so much pimples, but hairs, I guess. The imagery, not so good there. Exactly. Yeah. Let's go back. Let's go back in time. Look at the red light. Beep, beep. Okay, the hair in the back of your neck. All right. The little Men in Black reference. All right, no love. So what we got here, if only I had a way to simultaneously flip the bits and to add 1. Oh boy, I gotta build another circuitry to do the flip the bits, and another circuitry to add 1. If only I had somebody who could be some days an inverter and some days just a buffer to let the numbers pass through based on another bit. So if I had a box, I want to buy a box that if I put in that one bit is, okay, be the same. So let the value of B pass through because I'm just adding it, A plus B. But I also want the box to be able to flip B to invert all the bits. What would that box be? XOR. That box is a conditional inverter. Like I said last lecture. So I take my B, I pass it to my conditional inverter, I pass the subline to all those XORs, and that B becomes not B. But wait, you forgot the add 1. You forgot you got to flip it and add 1. How could I add 1 to this system when I want to subtract and add 0 when I want to just do a normal add? Carry in of the lowest bit. It's the same guys, right? I have this dead flopping input. Like, I wish somebody would plug into me because I know what I'm going to be as the lowest order bit. Normally plug into 0, right? Normally ground that guy to 0 because you don't feed anything in. No. If you feed in the subtract line, it adds the 1. So I flip it and the B and the flip and then with the subline and the A plus negative B. Tell me this isn't the coolest thing. Come on, guys, give me some love for this. Not me, that. Give that some love. Folks, this is off the hook. This is off the hook. This is awesome stuff, folks. I think this is one of the coolest parts of this whole lecture. To close it off with this. And this is it. There's your ALU. What an extremely clever adder subtractor. And thanks to Rachel for asking about it as the plant. There it is. So, clickers out at the ready. Bam! How about that for a way to close out the Dan Garcia lectures? Question number 1. Truth table for the mux with 4 bits of signals has 2 to the 4 rows. And we could cascade 1 and 1-bit shifters. Ooh, the shifters, shift left, shift right, to make 1 n-bit shifter for SLL and SRL. Okay, true, false? Four bits of signals, the signal lines. You have data lines and signal lines. S stands for signal lines. So 4 bits of the side signal lines, okay? 2 to the 4th rows, okay? So let's get some love. Shh, this is the solo question. Clarification.
The n-bit shifter always shifts its input by n-bit, or can you choose?
I didn't tell you what the argument is, how to pass in how many to shift by. But assume that's handled as part of this as well. I'm basically saying, can I build the shifter to handle a normal SLL case? Can I build an n-bit shifter to handle n bits to be shifted to left or right by some other amount by hooking it up, the shifters, in a standard way that I have for the adder and for the muxer, in a similar kind of way, by cascading them together somehow. Okay? Okay? So now, talk to your neighbors. Go. Any admin things to mention at all before? Okay. So let's come on back. Let's try it again. Yoink, go. All right. Okay, let's see how you did. I think there was not much change. Actually, quite interesting. So let's see what we have here. So I think I have a hidden slide here with my answer. So let's see what we got here. So the first one is supposed to be a nice animation or something. Oh, okay. So that's not so good. 2 to the 20 rows. That's more than 2 to the 4. And last one. Okay. So you can cascade them with the right circuitry to cascade to pass them the right number of ways, but that's a very valid way to have the shifters work because they just go left and right and it makes big sense. False and true. I'm looking for a B. So let's go back to the display here. And my display, what'd you give me here? Hey, too easy. Too easy, guys. Well done. Okay. So, in conclusion, bank. Muxes are a way that we're going to use when we see the control and data path, mostly data path, to choose among 2 inputs. Mostly those are 32-bit wide, guys. Muxes can be implemented hierarchically if I wanted to. That's a powerful thing. ALU can be implemented via a mux and some clever circuitry. And you can take the adder-subtractor block and make it n 1-bit adders with clever wiring of their carries. Okay? We'll see you on Friday when we start data path and control. Awesome.